So in the previous videos, I introduced you to my favorite feature importance technique, namely permutation importance. Now in this video, I want to introduce you to my favorite feature selection technique, namely sequential feature selection. Yeah, and sequential feature selection is also part of the wrapper methods that we started discussing in the previous videos. So we already checked off the filter methods, we talked about embedded methods, and we started talking about wrapper methods. For example, we saw recursive feature elimination. In this video, we will be wrapping up this big topic of feature selection by introducing sequential feature selection, my favorite feature selection technique. But before we get started discussing sequential feature selection in more detail, I wanted to ask you the following question. Which feature selection technique would guarantee optimal performance? So here, what I mean is, how do you find an optimal feature set? So maybe pause this video and think about how would you design a method that guarantees you to find the optimal feature set for your classifier. Yeah, so how can we find an optimal feature subset? After thinking about this for a little bit and coming up with interesting ideas and solutions, let me share my solution with you. Actually, the answer here is quite simple. So the idea or the approach to finding an optimal feature subset that guarantees optimal model performance is really just trying out all possible feature combinations. And we will call that an exhaustive feature selection approach. So how does that work, or what do I mean by that? So if you consider our favorite dataset, the iris dataset, we have 4 different features: sepal length, sepal width, petal length, and petal width. And how do we find out what is the best combination of features for our model? The answer would be trying out all possible ones. So in this case, we have 15 possible combinations from a subset that consists only of one feature, like feature 0, 1, 2, and 3. So these are the feature indices, by the way. So this would be feature index 0, feature index 1, feature index 2, and feature index 3. So we would try out all these different feature indices, or combinations of 2 indices, combinations of 3 indices, and lastly the full feature subset here. So it's really just trying out all these different combinations and seeing what works best for our classifier. Of course, this could be also very prone to overfitting, which is why it's important to use a validation set here, or even better, k-fold cross-validation when we try out these different feature subsets. And yeah, in the next video, I will also show you an example how we can do that programmatically. But yeah, before we see how exhaustive feature selection works in practice in the next video, let me get to a little limitation of this approach, which will then motivate why we are interested in sequential feature selection. And in order to introduce this limitation, let's take a look at how we can compute the possible or the number of possible feature subsets. So we compute these combinations or possible subsets using the binomial coefficient. You probably also know this as n choose k, where n is the number of items in my set and k is the size of the subset that I want to choose. In this case, I used different letters. I have, instead of n, I have m, and instead of k, I have I, where m is the number of features, so the total number of features in my data set. In this case, if we consider iris, this is always 4, so we have m equals 4. And I is the size of the feature subset that I'm interested in. For example, I can say I'm interested in only 2 features, then I would set I equals to 2. And if we are interested in all possible subset sizes, so subset size 1 to 4, we have actually a sum here. So we consider selecting 1 feature, then we consider selecting a subset of 2 features, 3 features, 4 features. So this is illustrated here at the bottom. So when we only want to select 1 feature subset, we have 4 choose 1. then if we want to select, let's say, two features as the subset, we have for choose 2 and so forth. And if I sum this up here, I get 15 as the number of possible combinations for different feature subsets using, let's say, the iris data set here as an example. Now let's consider a different data set that we have already talked about, or that we have already used in the previous videos, the wine data set. So we have here the wine data set where we have 13 different features. The approach to computing the number of combinations is still the same, but yeah, you can already see that this would become more expensive because we have now more different feature sizes. And also, yeah, there are more ways, let's say, to select 2 features out of 13 than there are ways for selecting 2 features out of 4. And for example, if I would compute the number of possible feature combinations, I would come up with 8,191 in this case. So as you may have already guessed, one problem with exhaustive feature selection is that it is very, very expensive, especially if we have large feature sets or large number of features in our data set. And this motivates the development or the use of sequential feature selection, which is, you can think of it as an approximation technique that does not exhaustively evaluate all feature combinations, but only a subset of those. So this is essentially like we can call it a greedy search or an approximation or a heuristic instead of doing this exhaustive search. So how does sequential feature selection work? It's actually a pretty simple technique, but if you, let's say, would try to draw it out, it can be quite confusing. Here I have actually a figure from a paper I worked on with my collaborators last year. And I put a lot of time and effort into making this figure, so I wanted to reuse this figure here for this lecture. And no worries, I realized that this looks really overwhelming here, looking at everything all at once, which is why I will break this down and walk you through this step by step. Yeah, so let's start with steps 1 and 2. And previously I mentioned the term sequential feature selection. So why does the title of the slide here say sequential backward selection? Sequential backward selection is a special case of sequential feature selection. And I will later on show you also other special cases. But to keep things simple, let's start with sequential backward selection, which is maybe the most common type of sequential feature selection. And step 1 here would be starting with the original feature set, which consists of 29 features in this particular data set. This is a data set that we have used in this particular paper, but if you think about, let's say, the wine data set, we would only have 13 features. But let's maybe stick with the 29 here, the original features in the paper that I previously mentioned. So here the different features have, let's say, very weird names. This is very special to the data set that we worked with. So for simplicity, you can also maybe think of feature 1, feature 2, 3, 4, and so forth, up to feature 29. And this would be our starting condition, that we use all the features that we have in the data set. And then in the first iteration of sequential backward selection, what we do is we generate all possible feature subsets of size n-1. So in this case, it would be 28. So 29 minus 1. And how do we do that? Yeah, we essentially take the full feature set and just delete one feature at a time here. So we create all the different feature subsets consisting of 28 features. And then once we have these different subsets, we should have 28 subsets in this case, feature subset 1 to 28. What we do is we evaluate each candidate feature subset by, let's say, using k-fold cross-validation as an example and record the performance of that subset. Okay, now we are ready for steps 3 and 4. So in the previous step, we talked about creating the subset of size 28 by just removing one feature at a time. And we also evaluated the performance that we get when we evaluate one feature at a time. So let's say we get something like 93% accuracy for that feature subset, 98% for that feature subset, and maybe 91% for that feature subset. Now, after we have all these performances, we scan these and see which one gives us the best or the highest performance. Let's say we find it's this subset with 98% accuracy, so subset 2. And all step 3 is really about is removing that feature here permanently. So removing the feature that is absent from the subset with the highest evaluation score. It just means that now we focus on subset 2. So going from step 1 to step 2, we removed one feature. We went from 28 to from 29 to 28. Now, iteration 2 in step 4 is essentially the same step. It's essentially similar to going from 1 to 2. We again just remove one feature. So we make this size from 28 now 27. So we remove one feature. It's exactly the same approach going from 1 to 2, except that we start now with subset 2, the best subset from the previous round. And this is why it's called sequential backward selection, or we can also think of it as an iterative process where we remove one thing at a time. And each iteration is really just the same. We are just using the previous subset for the next round. So here, similar again, we are removing one feature at a time. We are now creating smaller subsets, 27. And again, we would evaluate the performance of these subsets. So let's say we get maybe 94% accuracy, maybe let's say 97% accuracy, and here maybe 99% accuracy. And then we would again select this feature subset. So we would select last one here, and then repeat this procedure until we have our desired feature size. All right, let's then wrap up sequential backward selection. So we would be repeating steps 3 and 4 multiple times until the feature subset contains only a single feature. So this means that we would be evaluating these candidate subsets to select the best performing one, select or delete one feature at a time, and then again select the best candidate subset and so forth until there's only one feature left. So we start with 29 and we stop when we have only one feature left. And if we do that, we will have n-1 iterations where n is of course 29. So we will do this n-1 times, and then we will consider all these n-1 iterations and select the final subset as the subset with the highest evaluation score. And in case of a tie, we would select the smaller feature subset. Why the smaller subset? Yeah, because it's simply computationally more efficient to use fewer features. And also in practice, if you think about collecting data, collecting fewer features is always simpler than collecting more features, right? So we would, in the case of a tie, select the smaller subset. But yeah, and overall, the procedure here is to find the optimal subset is by repeating this process of deleting one feature at a time until only one feature is left. In special cases, you may be interested in having at least, let's say, 3 features or 4 features. So you can also stop this early. You can say maybe only 3 features or something like that. So it depends really on what your limit is, your lower limit for the feature subset size. If you want to, let's say, get the best possible results from sequential backward selection, you would really run it though until only one feature is left and then look at all the subsets. And we will be doing that later in the code examples in the next video and see how that works. Yeah, now we covered sequential backward selection. And like I mentioned before, there are different flavors of sequential feature selection. Sequential backward selection is maybe the most common one. Another common one, though, is sequential forward selection, which I want to introduce in the following slides. So sequential forward selection is actually pretty similar to sequential backward selection. So in sequential backward selection, we remove one feature at a time. In sequential forward selection, we add one feature at a time. Starting with an empty feature set, we grow the feature subset until we have the maximum number of features reached. So I'm trying to illustrate this here with a slightly smaller data set. So instead of, let's say, using 29 features, we have a smaller set consisting of 4 features. In backward selection, we would remove one feature at a time, but here we are not doing that. We are growing the feature subset. So what we do is we consider in the first round, we consider only one feature at a time. And for each feature, we train the classifier only on that given feature. So let's say we train a classifier on feature 1. We then evaluate its performance. We do the same thing for feature 2 and so forth. So like before, we would get different performance values. Let's say 98% accuracy, let's say 99% accuracy, 97, and maybe 93. Then again, we would select the best subset from these different feature selections or feature evaluations. So in this case, 99 is the highest accuracy, so we would select feature number 2 for the next round. So the next round would then start with feature 2. And again, we would add one feature at a time. So we have now feature 2 and 1, feature 2 and 3, feature 2 and 4. And again, we would select the best feature here. And we would do this until we have the maximum number of features reached, like the 4 features shown here. So you may wonder now, what is the performance of this approach? Not the computational performance, but the performance in terms of finding the best feature subset. So here I have some plots from a paper called Floating Search Methods in Feature Selection. And I will also introduce what the floating means in an upcoming slide. But let's focus now on just the regular sequential feature selection. So here we have sequential forward search and sequential backward search. And we also have the optimal feature selection method here. Optimal here means exhaustive feature search or feature selection. This would consider all possible feature subsets. And you can see, the optimal performance is this dotted line here. And considering sequential forward selection, it's of course not as good because we make a locally optimal choice. We are not considering all possible subsets because it's a sequential search where we make a locally optimal search or choice. And in this case, you can see there is quite a gap between optimal and sequential forward. By the way, these other ones here are genetic algorithms, and there's also something called max-min search, which is actually not very good, so we are not going to talk about it. These genetic search algorithms are, I would say slightly better than sequential search, but they are also more expensive. So here we are only focusing on sequential forward and backward selection. And here again, for reference, we have the optimal search. It's the same as on the left plot. But now we have, for comparison, sequential backward selection here, this star. Let me use a different color. So you can see actually that in this case, the performance between the optimal results and sequential backward selection are identical. And here at the bottom are 2 plots showing how expensive these different methods are. So you can see SFS, sequential forward selection, is pretty cheap. So the lower, the better. It's the time in seconds. And sequential backward selection is also pretty cheap. So here the bottom line is that there are methods that are more powerful. I mean, the most powerful method is, of course, the optimal search, the exhaustive one, but it's also the most expensive one. And if we have large feature subsets, it's often not feasible to run this at all. So we use approximation methods like sequential feature search. There are the genetic variants here, genetic sequential forward selection and so forth, but they are very expensive. Cheap versions are sequential forward and sequential backward selection. And in this case here, sequential backward selection actually gives you even optimal results on this particular data set here. So the results for different feature subsets are identical to the optimal results that you would get by running an exhaustive search, which is actually great news. Yeah, now the interesting question is when to use forward selection and when to use backward selection. If you are just interested in the best performing feature subset, it might make sense just to focus on backward selection as you have seen in the previous plots, because it can find feature subsets of optimal performance. Now, if you are interested in a fixed subset size, then I would differentiate between forward and backward selection. So consider you have a dataset with 100 features, and it's too large really to run exhaustive feature search. And for some reason you are interested now, let's say, in a subset of size 5. In this case, I would run forward selection, right? Because that will be faster to run than backward selection, because yeah, you start with one feature, then add another feature, another feature, another feature until you reach 5. So you have only 5 steps here. With backward selection, you will have many more steps. You will have 95 elimination steps. However, vice versa, let's say you're interested in 95 features. Here it might make sense to run backward selection, because then you only have a smaller number of elimination steps, because going from 1 to 95 using forward selection will be 95 selection steps, which would be very expensive. And this way you only have going from 100 to 99 up to 95, which is much more efficient in this way. Okay, so now we talked about sequential backward selection and sequential forward selection. But also in this plot, or based on the title of the paper that I've shown you, there are also 2 more things. One is called sequential floating forward selection, and one is called sequential floating backward selection. So what are those? All right, let's now make sense out of sequential floating forward selection. Sequential floating forward selection is very similar to regular forward selection, except that there is an optional or additional floating step. And before I show you this optional floating step, let me, for reference, show you the regular sequential forward selection. So here there is no floating selection, it's just the regular sequential forward selection. For this example, we consider a data set consisting of 6 features here. And suppose we have already completed rounds 1 to 4, and this is the feature subset after round 4. So we have selected feature 2, 3, 1, and 4. So the only features we have not selected are 5 and 6. So the regular round 5, so the regular round in normal sequential forward selection would look like as follows, where we would add feature 5 to the subset, train the classifier, and evaluate its performance. And then we do the same thing also for feature 6. So we have 2 subsets here that we evaluate, and we look at the performance, and then we would select the best performing one in the regular sequential forward selection method. All right, let's now see what this floating is all about. So the floating in sequential floating forward selection is an optional step, which would be removing a feature if it improves the performance of the classifier on that given subset when the feature is removed. So this is an optional step, and we carry it out at each round. So how does it look like? For reference, consider our original feature set again with 6 features. And after round 4, we have the following subset consisting of feature 2, 3, 1, and 4. Now, if you recall from the previous slide, what we would do in regular forward selection is we would select the next feature here. However, in the floating variant, we have an optional step where we optionally remove a feature if it improves the performance. So here in this example, we would, similar to backward selection, we would remove one feature at a time. Again, train the classifier, get the performance, and then if the performance here is, for one of those, is higher than the performance on the original subset, then we remove that feature permanently. So for example, let's say we get 98% accuracy for that feature subset. If removing feature 3 results in 99% accuracy, we would remove feature 3 permanently at this step and then carry out a regular round 5 here, again with adding a new feature, but now with feature 3 removed. But we only do that if it improves the performance compared to the previous round. So why would actually removing feature 3 improve the performance? I mean, this can happen because the way we select things in sequential feature selection. For example, when we had only feature 2, we may have found that feature 3 is better, let's say, than feature 1 or 4. So we had then at that point feature 2 and 3 and added feature 1. And maybe there's a high correlation between feature 3 and 4. And this combination particularly works well, having both of them particularly works well with feature 2. And somehow feature 3 is now not that good anymore because it kind of like maybe became redundant, or it's not as useful. It's kind of maybe resulting in overfitting or something like that if feature 1 and 4 are present. So it really matters here in which order we select features. So if we have only feature 2 and 3, this might be better than feature 2 and 1. But in combination, 1 and 4 might be better together than having feature 3. And this is sometimes also called an epistatic effect. So in this case, the sequential floating forward selection has, let's say, more flexibility than sequential feature selection, the regular one without floating. And also it's better at considering feature interactions in this case. But in any case, any type of sequential feature selection is kind of like superior in terms of univariate feature selection, where you only consider one feature at a time, because here you really consider combinations of features. All right, so now we have also covered sequential floating forward selection. There's one more method, sequential floating backward selection. However, lucky for you, I don't have slides about that because I felt like it would become a little bit boring at this point, because this method is relatively similar to sequential backward selection, except that we have an optional step here. So in sequential floating forward selection, we have the optional backward step that we just discussed. And in sequential floating backward selection, we would have an optional forward step. And this is really it. So these are the main methods of sequential feature selection. Yeah, let me get back to the previously mentioned paper one more time. So in the paper, they also had a comparison between sequential floating forward selection and sequential forward selection. So the floating variant and the regular variant. And here for reference, this is the regular sequential forward selection. And here, let's say this is a measure of performance. And you can see that, for the sequential floating variant, we have slightly higher or better performance if we use this floating variant, but at the same time, of course, it would also be a little bit more expensive. And here on the right-hand side, the same results again with a larger feature subset compared to this one. So we can see the floating variants are slightly better than the regular variants, but again, this would come with an increased runtime too. So there's always the trade-off between runtime performance in terms of how long it takes to run the algorithm versus the predictive performance of the feature subsets. Yeah, so in the next video, I will show you how to use sequential feature selection in MLextend and scikit-learn. I know, though, that some people prefer mathematical notation over, let's say, conceptual drawings. So I wanted to already show you the MLextend documentation here, because I added the mathematical notation for sequential forward selection, and also further below here, which is not shown here, sequential backward selection, sequential floating forward selection, and sequential floating backward selection. So if you are interested in, let's say, the mathematical notation, please go to this website where I have the algorithms in, let's say, more mathematical notation. And again, like I said, in the next video, we will take a look at the code examples. So yeah, the next video will be on the code examples, and then we will have finally reached the end of the feature selection lecture. And then in the next lecture, we will also talk more about feature extraction.